Hello and what's up to you all, Mindsetters? It is a lovely Tuesday. I hope you all relaxed. You had a great day at school. Share with me on Facebook. My name is Abram, and I'm here with John to give you the best life science show for grade 10s
Life
ever.
science.
Sorry, physical sciences.
Science, please.
Where am I, John?
You're one day ahead, I think.
Okay. Anyway, I just wanted to see the look on your face. We're doing physical sciences, Mindsetters. John, how are you?
I'm fine, thank you, Avram. Of course, it's physical sciences, guys. It's Tuesday. It's the day to get excited, and today we've got an amazing topic. The topic of magnetism.
Awesome, awesome.
Are
I
you
see
magnetic?
we're also gonna do some experiments. Hey, am I magnetic?
Yeah.
I think so. But
We'll have to test and see how magnetic you are.
Yeah, no, we'll do some tests.
Okay.
Well, Mindsetters, all you need to do is to get your notes, download them or view them. We've got two options available for you guys. And already they are posted on facebook.com/learnextra. Like our page, share the page join the 76,000 Mindsetters that we have already. It is a big community, and we also want you to take part by helping other Mindsetters on the page. Also follow us on Twitter @learnextra. And let's enjoy the show, because we also have a challenge question just for you guys.
Right, guys, good to be with you. Now, let's have a look at what we're going to do today. We're going to start off by looking at the topic of magnetism. And the first thing we're going to do is we're going to describe some magnetic materials and describe what magnets are, basically. We're then going to look at some drawings of a magnetic field around different magnets, and we're going to discuss applications of magnetism. So, Abram, just want to open it up to you. You any idea where magnets are used in everyday life?
At the bank, they
bank?
also use them for coins.
Anything else? Come, you're a music guru. Come, think about it. Okay, guys, I want you to think about it at the same time. So, where do we find magnets every day? Now, Abram should be thinking about this and listening to music and all that sort of thing. There's some funky ideas about where we find magnets. And here's another interesting question that I want you to think about. This is not geography, but it's kind of a bit of a spin on geography. So, a compass needle, which is in fact a little magnet, always points to what we call north. What does this tell you about the nature of the Earth's magnetic north pole? Okay, so think about it. If I look at a magnet and I have a little plotting compass here, or a little compass, and it will always point north. Now at the moment, if I look at it in the studio, north is in that direction over there. Okay, so it's sort of in that direction. The compass needle is pointing in that direction. You can't see it, it's too small. But what does that tell you about this little compass needle and about the Earth's magnetic field? Think about it, and let's see if you can get some responses. I've already posted the challenge question. Is it up at the top of the page? It's up at the top of the page on the Facebook page. Give your answers as comments below so we can see who's getting the answer. The other thing I'd like you to comment on is, where do we find magnets? Any use of magnets that you know about, put them in there and we'll take a look at them as well. Okay, so what I want to do before I get into the summary notes about what magnetism is, I've set up a few little samples of magnets and magnetic materials, and I want to explore which things are magnetic and which are not. So if I take this rod here, it's a cylinder made up of aluminium. What do you think, Abram? Do you think this will be magnetic, or do you think it won't be?
I don't think it will be magnetic. Let me see. I think it will be magnetic.
It's metal. Now, guys, some people think that all metals are magnetic, but that's not necessarily true. We're going to explore that and have a look at what magnetism is, and let's start by testing. Now, come with me, and I'm just going to go over here, and on this piece of paper in front of me, I've got some metals. This is lead foil, this is some zinc, this is some copper, and here are some paper clips made from iron or steel. And there's my aluminium. Now, I want to bring my magnet in, and straight away, I hope you can see what happens. As I bring my magnet closer to these paper clips, let me just bring them a little bit more to the middle. Can you see what's happening? Abby, can you see what's happening? What's happening to the paper clips? As I bring the magnet closer, Can you see?
There's an attraction. And
There's an
it moves.
attraction.
Yeah.
And if I'm at a distance, I can get them to actually jump. If they're close enough to them, I can get the paper clips to turn. Now, guys, that's not magic. It's just magnetism. Let's see if we can do the same thing with a little bit of lead foil. I'm going to even make it small and cut it off, and so it's not as heavy. And all that's happening is these paper clips are getting in the way. So can you see there's nothing happening there? There's nothing happening with the lead foil. There's nothing happening with the zinc. There's nothing happening with the copper. And even the aluminium that AB thought might be magnetic, now it's going to roll, watch. And that's not going to, but it doesn't stick. It doesn't stick. It falls off. If I did the same with the paper clips, they stay on. And here's another interesting thing. That paper clip, now I can even make a chain of paper clips and get them to extend further down. Isn't that amazing? So that the one paper clip has now started to attract the other. Now, that was using this magnet. I could use another magnet and find that magnets attract each other, or they will repel each other. This one seems to just be attracting the other one because I think this is very weak. We can see that over there. It hardly picks up the paper clip. I've really got to go close to it for it to pick up the paper clip. Now, there's one last thing that I want to do, and that is just to bring some iron filings. Now, iron filings are really just little powdery things of iron cut up. And iron is a magnetic material. Let me show you that it is magnetic. Even with this weak magnet, oh no, let's do it underneath. This weak magnet, we can get an interesting pattern. I don't know if you can see. Let me try it with a stronger magnet. Ah, look at that. Putting the stronger magnet underneath it, and now I can even turn it up, and the iron filings are stuck to the paper. As the magnet moves, the iron filings move with it. Can you see that? Isn't that amazing?
It is,
Hey?
hey?
It's really quite cool. Now, what you can't see here on the flat screen of the television is that those little iron filings are actually standing up above the paper. They're not just lying flat. So what we need to recognize is that magnets create all sorts of interactions with other materials. And this is quite an interesting thing. They don't have to be in contact. And so what is magnetism really? Let's go and have a look at the notes and go through them in some detail. So the first thing that you need to know is that magnetism is a property of certain materials that allows them to exert forces on each other, not necessarily in contact. When the paper clips were down on the piece of paper, we put the magnet above it, it jumped up. And even that one paper clip became a magnet itself and was able to pull up the second magnet. There are two types of magnetism, temporary and permanent magnetism. So for a moment, that paper clip was a magnet. If I had to reach over and get that paper clip now and just get another piece of iron filing and try and stick the iron filing to the paper clip, nothing's going to happen. This is no longer a magnet. It was only a magnet when it was in contact with the other magnet. So that's a temporary magnet. The permanent magnet was the ones you saw, the red and silver bar, and also those graphite magnets, or they were a brown sort of color. Sorry, not brown, a black sort of color. Those were magnets. They're baked magnets. Okay. We explain magnetism by describing a magnetic field which surrounds all objects made of magnetic material. So this is the important part that you've got to understand. Around every magnet, there is a sphere of influence. Okay? It's a region of space. Now, please remember this is three-dimensional. It's not just flat on the piece of paper. You saw those iron filings take on a pattern around the magnet. Now, if you tap them, you can actually get a very nice pattern that is very similar to the one we're going to draw a little later. But we're not going to worry about that now. This illustrates the magnetic field, where the particles are in touch with each other, where the magnetic material is in touch with a magnetic field. So around a bar magnet, there is a magnetic field. There's a region in space. And if I bring something else that is magnetic, either another magnet or a magnetic material like iron or nickel or cobalt or one of those are the three main ones, bring that into that area, it will be influenced by that magnetic field and will either be attracted or repelled. And so that's what we're saying. A magnetic field is a region in space where a magnet or objects made of magnetic material experience a non-contact magnetic force. Non-contact means they don't have to be touching. Okay? Very important that you understand that. There are some other non-contact forces. Here's one that you might have thought about. If I let this little bit of lead, a lead sinker, fall, okay? What made it fall? Well, there's a non-contact force of attraction with the Earth. So there's a gravitational field around the Earth, and anything that's got mass will be attracted to it. In the same way, anything that is magnetic, like a magnet, will be attracted to in a magnetic field. So if you've got a magnetic property and there's a magnet, you'll be attracted to it. So bear that in mind. So what we need to recognize is that the strength of the magnetic field decreases as one moves further away from the object. So even if I took that little paper clip here now and I held it in my hand, it wouldn't be experiencing the force of the magnet over there. It's too far away. The magnets generally act over short distances, except that there are some that are very strong and they exert a force over a bigger distance. But even so, it's usually over a short distance, close to the other. Now, to explain this phenomenon of magnetism, you need to understand one thing, and that is that where does it come from? We've seen it on the big scale. So what makes it? Where are we? How can we explain it? And scientists really struggled for a long time. They thought this was some spooky magic. Just like the topic that's related to this called electrostatics. Electrostatics, which we'll deal with next week, also was kind of scary and people didn't understand it. Magnetism, they kind of just accepted, no explanation, until we started to find out about the atom. And what we recognized is in the atom you have a nucleus, which is a positively charged object, and a negatively charged electron or series of electrons that orbit or move around the central nucleus in different patterns and different ways. Now, what scientists didn't know until about the late 1800s was that if you have a moving charge, around every moving charge, a moving charge creates a magnetic field. So where do things that are magnetic or are magnetic materials, where do they get this special property from? Well, it comes right from the microscopic view, right down at the center. Every atom has a little magnetic pole. It forms a little, what we call dipole. And these dipoles arrange themselves together quite randomly. We call these regions magnetic domains. And so the domains are arranged randomly, and the net effect, the overall effect, is that although Abram said at the beginning, is he magnetic? Yeah, he's magnetic. He's made up of atoms. But overall, those magnetic material, those little atoms that are magnets, tiny little magnets, those cancel each other out. So we ourselves, apart from the iron, little bit of iron that we've got inside, are mainly non-magnetic because the domains aren't aligned. Let's just go through what that means. So very carefully, very quickly, we recognize moving charge, examples of they're arranged randomly, and we said magnetic fields around can be aligned to point in the same direction. And examples of these magnetic materials are cobalt and nickel. Now, I think that I've got just two more things to say, and that is that a permanent magnet is made of magnetic material where the domains are all lined up. And we have one end that is called north and the other end that is called south. And the important rule about how magnets interact is that like or identical poles repel each other, while unlike poles or opposite poles attract each other. Very important rules in the notes are about representing the magnetic field, and I haven't got time to go over them, but I suggest you read them, and we'll practice these when we do one of the questions. Okay? So I hope that's been a brief introduction and summary of magnetism, what makes magnets, and hopefully you have a clearer picture about magnetism.
And I must say, I'm learning a lot here, John. Already I've learned so much.
Okay, good.
I hope the mindsetters are also learning. If you have some questions, make sure that you send them through on facebook.com/learnextra. I see you guys on the page, Lungelo, Banyana, Tato, welcome guys. And tell all your other friends to tune in also as we learn more and learn extra. The challenge question is on the wall, so give us your right answers. We'll see you after the break. Welcome back, Mindsetters. I hope you are enjoying the show with us, and make sure that you get your notes on facebook.com/learnextra. The links are up there, or you can get all the notes that we have on Mindset at learn.mindset.co.za. It's very important, Mindsetters. It's learn.mindset.co.za. That's where we have all the notes, even for the shows that are still to come. You can still get your notes in advance. But otherwise, last week we were running a competition sponsored by Casio, and we have our winner for the Grade 10 show, and our winner is Sipo. So Sipo, congratulations to you. You have won yourself this awesome Casio calculator. Back to you, John.
Thanks so much. Now, guys, don't go away. I want you to learn from today's lesson, and I will be posting today's competition after the show. So make sure you concentrate, and then let's see if you can enter and win a Casio calculator yourself. Let's go to the Improve Your Skills questions now. These are in the notes. Hopefully you've had a chance to have a look at them, get them on your phone, or get them downloaded and print them. Let's have a look at them together. We're told the diagram below shows 2D. 2D, remember, means flat representation of a magnetic field formed around a bar magnet. So what it's showing you is I'm just going to go over it. There's your bar magnet. And now it's got a whole lot of lines going from it. And I just want to go over these as well. So just to illustrate, there's one coming this way, one coming that way, one coming that way. Now, they shouldn't overlap. They shouldn't cross each other. And they should have arrows on them. And in case you can't see, the arrows are pointing in that direction like that. They're pointing in that direction like that. They're pointing towards that one and away from this side, away from that side, and coming out like that. Got it? Now, with that information, I think we can proceed, and we can say, identify where the magnetic field is strongest. Now, what we need to recognize is that the picture that we draw here with these field lines gives us a very good indication of where the magnet is strongest. And even from our little experiment, you should recognize that at the ends of the magnet, we call those poles. Those areas are the strongest areas. So this area here, which I'm just wanting to get a little drawing of so it doesn't have a fill on the inside, I want you to see that area there has got lots of magnets, lines going through it. And that area there, around that space over here, that's where there are lots of field lines crossing through that region, through that area. That is then the strongest region. Now, what else can we say? We can say over there, look, you've got lots of lines, and they're close together. Two aspects, lots of lines passing through a space, and over here, notice, you've got fewer lines. You've only got 3 lines. Same thing over here. So it's strongest in this region. This is where it's strong, at the pole. And it's strong over here. But it's weak where the lines are further apart and there are fewer of them. So that's where the magnetic field is weaker. So let's just see. Where was it strongest? Where's the magnetic field weak? Well, we've answered both those questions. Excuse me. Now, the next part that we need to do is we're asked to label the north and south poles. Now, how do we know which is north and which is south? Well, there's a very simple rule. And this is how we would plot around a bar magnet. And I want to just show you so that you can get it right for yourself. If that's a bar magnet, then what we would do is we would first of all take a little plotting compass. And we would take our little compass, which is a little circle, and it has a little arrow on it. Now, let's pretend that this is the arrow and it's pointing in that direction. And I'll just put an arrowhead on it. It points in that direction like that. Now, if I take this virtual compass, I'm going to show you how we were going to use it. We're going to group that together. I want to group it. Just let's group it carefully. Right. Put it over there. It's going to point in that direction. So the field line that we would draw over here would have a direction, and it would point in that direction. If I moved this plotting compass to another position, let's say I moved it, and that's why I said it's a virtual little plotting compass. If I moved it to over here, then that's the direction it would be pointing in, and I would draw my field line doing this. It's now going to go in this direction. And so wherever the line draws, wherever the line points, the arrow points, my north pole points, that's the direction of my field line. So I'm going to draw it, and I'm going to say it's pointing in that direction. So everywhere, at every point along this route, I'm going to take the direction that the little compass needle points in. And if I brought it all the way around to here, if I brought it all the way around to the bottom over here, it will be pointing back in that direction. So with that in mind, what you've got to recognize is the compass needle always points to north. So that means it's the arrow end of the little compass, my arrow end itself is a little north pole. It's pointing to north. So if this is a north pole, then the compass needle is repelled from that side, and it's being attracted to the south end. So that's north and that's south. So it goes away from the north, and it comes in at the south. Away from the north and in at the south. So if we go back to our drawing over here, where is it going in? It's going in at this point over here. So that end is south. It's going away from the north. So we've labeled the magnetic poles according to that principle. Take your compass needle. The compass needle will give you the direction of the field line. And you can do it very practically. Get yourself a little plotting compass, get a piece of paper, and you put the magnet underneath, and you move your compass needle around, you move your compass around, just draw little arrows, and join those arrows together, and you'll get your field line map, which really tells us where the magnetic field is. Okay. Now, question number 2 tells us that we're to represent the magnetic field formed around 2 magnets where the north poles are facing each other. Sure. And what would you feel if you were holding one of the magnets? So let's get this drawing right, and then we can come into it, answer the question. So there's my magnet, and here's another one. Now remember, when we're drawing these, what I said just now. I said that that's a north, that's not a south, that's a north as well. This is a north, north. Now we've got to draw the field line pattern. Remember, it goes away from the north. So if I start to draw this away from the north, what I'll recognize is that there's one coming from here as well. So what happens, these magnetic field lines can't overlap each other. They've got to do like that. They've got to separate. They pull each other away, they repel each other. When you get a pattern like this, we're saying there's repulsion. They don't cross over, but they still come in on this side, still come in on this side. We're not really worried too much about the south end. We weren't asked to do that. But I need you to understand that they're always coming in at the south end, from wherever, coming in at the south, coming in at the south. Okay. But between the north, when you've got two north poles or two south poles facing each other, you'll get this tension between the magnetic fields. They can't overlap, so they compress. And when they compress like that, in a small space, you'll get stronger and stronger magnetic push. A stronger and bunched field lines together, bit like contour lines. And if you do geography, you'll know this, when lines are close together, contour lines are close together, it's very steep. Here, when lines are close together, very strong field. So, to answer the second part of the question, what would you feel if you were holding one of the magnets? And to explain your answer, well, you would feel a force of repulsion. And the reason is because there's a very strong field. If you've tried to push them together, that field pushes together like we've shown there in the field lines. Those field lines, remember, are imaginary lines. They're not real, but it gives us the impression of what's actually happening inside there. Okay, now let's have a look at the third question. And I've almost answered it by my drawing. It says, it is possible to find a region in a magnetic field where a magnetic object will experience no force. So draw a diagram to show how this is possible. And the next part of the question, what would you observe if you placed a compass at that point in the magnetic field? Well, the answer is right there. That point is known as the null point. Okay? It's known as the null point. The field kind of pushes in all directions. So what's a compass needle going to do? It's very interesting to see. If you've got strong enough magnets, that little compass needle doesn't know which way north is. And notice something here is that the local field overrides the Earth's magnetic field. So even though the Earth's magnetic field is really strong and can cause a compass needle always to point to the North Pole, even though magnetic north is far away from us, but when you've got a local field of two magnets pointing together, what happens is that needle can't find a North Pole to settle on. So for 1 minute it thinks it should point in that direction, and another it thinks it should point in that direction. And there are all of these forces acting on that little needle. And so that needle gets pushed and pulled and pushed and pulled, and so it begins to spin. And that's exactly what happens in the middle. Now, what you need to be able to do is not only draw the picture for repulsion, but you should be able to draw it for attraction. And what would attraction look like? Let's just pick that one up for a second, so at least you've seen it. Well, when you've got attraction, this isn't in the notes, and I hadn't planned to draw it, but seeing we've got a bit of time, let's draw it. You've got a north pole on that side and a south pole on this side. Then the field line would go directly between those two, straight. They will touch the surface at 90 degrees. This is a very strong magnetic field and would cause the two magnets to pull each other towards each other. Doesn't matter if that was south and that was north, the field lines would be in the opposite direction, but it always runs from the north to the south. So we need to recognize the direction in which the compass needle will point. Always ask yourself that idea. Okay, I think we've got time for one more question. I've answered this one. We drew the diagram. I showed you the null point. The last thing says, is it possible to make a magnet with only one pole? So let's do a thought experiment here. If we take a little bar magnet and we said to ourselves that this end is north and that end is south, and we cut it, and we cut it into two. Now, if we cut it like that, and we cut this end like that, we would think for ourselves that that end would still be south, and that end would definitely be north. But what happens at this end over here? What happens over here? What happens over here? Think for yourself for a minute. What would happen? Well, maybe you're thinking that this end should be north and that end should be north as well. If that was the case, then we'd have two poles that are the same, and this would pull it apart. They would push away. But in the nature of things over here, there's no force pulling this bar magnet apart. So in fact, if we cut down there, there's something holding this end to that end. They want to stay together as one piece. And if they want to stay together as one piece, then they must be opposite poles. And so the argument goes that must be south and that must be north. I haven't really explained why. So that's the original explanation. Doesn't matter where you cut a magnet, it wants to stay as one piece. But why is that the case? Well, it goes down to the microscopic level. And it doesn't matter how small you go. If you were to go right down to the bottom of the atom, you go very, very small, so you only had one atom, one end of the atom. Let me just draw it as a circle. So if we went microscopic, we would have a domain, and we could represent that kind of as the atom. In the domain, we would have one end as being north and one end as being south. You can't get smaller than an atom. An atom is the simplest and the smallest part of matter. And one end of the atom will have a magnetic north pole, and the other end of the atom will have a magnetic south pole. So even if we had 10 atoms, they would all be aligned because it's magnetic material. And it doesn't matter where we cut it. We can't cut smaller than an atom. So there would always be one end would be north and the other end of the magnet would be south. So it's not possible to get a single pole. It's like you can't get day without night. You can't experience a north pole without a south pole. Now, the opposite of that is that we know when we deal with electric charge, you can isolate a negative charge. You can isolate a positive charge. But with north and south, they always come in pairs. And that's quite interesting. I hope you find that interesting too. Abram?
You also can't learn without having a break.
Yeah, maybe that's true.
Well, my sisters, thank you for the questions that you guys are giving us. And John later on is going to answer those questions. And the challenge question is still on the wall, so make sure that you answer that. We'll see you after the break. Welcome back, Mindsetters. Now, for the Mindsetters that are still looking for the notes, remember you can download all our notes on learn.mindset.co.za. But for today's show, they're already posted on our wall and the challenge question. And some Mindsetters already, John, have given us their answers.
Okay, let's hear some of those answers, AB.
Okay, Ananya says that the reason it's that the north magnetic poles move over time due to magnetic changes in the Earth's core.
Okay, we'll come to that. I'm not going to tell you whether it's right or wrong just yet.
Okay, Pamela Hope. The Earth's magnetic north pole is attracted by the Earth's magnetic south pole.
Okay, a bit confused there. I'm not exactly sure what we're saying, but we'll try and clarify.
Okay, at the North Pole, magnetic field will attract each other due to the changes of the South Poles, where they will repel each other because the magnet only attract each other by the ferromagnetic.
Oh, that's a lot of stuff that's been said there, and I'm not sure how much is correct or not. Okay, so I tell you what, let's get some ideas going here. And the first thing that we're going to do is we recognize a compass. We're going to start off by talking about a compass. A compass always points north. So what is a compass? So remember, we've been drawing it, and I drew a little rough sketch of the compass earlier on. And I said we have this little circle, and in the middle of the circle, we have a little needle. And that needle is really a piece of let's not use that one. I want to use a full one. It's really a piece of steel that's been magnetized. Now, steel is made up of iron. Okay? Iron plus oxygen gives you steel. And it's a mixture. It's an alloy of forms that gives you steel. It's hardened by the oxygen. And this is, because it's got iron in, the symbol for iron is Fe, and we use the symbol or the prefix ferro when we're dealing with iron. So when we talk about ferromagnetism, we're talking about those things that have iron in them that give them the magnetic properties. Now, not every magnet is made up of iron. We need to understand it. Things also that are magnetic can be something like nickel and cobalt, and there are even some rare earth metals that they bake in a clay and they force them to become magnetic. So this is some of the new magnet technology that's available. You don't really need to know about it for grade 10, but if you're interested, go and look at, use a search engine like Google or Bing and look up rare earth magnets, and you'll find that they're really strong, and they're much stronger than the ferromagnetic magnets that we use with iron. Okay, so this little iron piece of iron that's floating on a needle is able to move freely. It spins around, and in fact it's a really nice thing for you to go and do, and I'm sure you might have done it before, is you can make your own magnet. You can take a pin, take a magnet, and stroke the pin in the same direction from south to north or north to south, so that the pin always goes in the same direction. The pin then will become a temporary magnet. The magnet is a permanent magnet. The pin, by stroking, can become a temporary magnet. It will lose its magnetism after some time. You then place it onto a piece of cork or something that will float, put it into a little beaker, and you'll see that it will point in a particular direction, namely the Earth's magnetic field. The important thing about a compass, though, is that this end of this magnet that is made of is the North Pole, and this end is the South Pole. And we're saying that it always points north. We're saying it points north. Hope you understand that for the moment. Okay? If we bring a bar magnet close to one of these, and we make the bar magnet that to be a north and that to be a south, then our little compass needle, that whole compass needle, is going to do something quite interesting. It's going to change its direction of pointing, and it's going to start to point to the local area of the North Pole, of this North Pole. Okay? It's not going to stay where it was. It's going to point to where the local magnetic north is. And the local magnetic north is in line with that. And so you can have a lot of fun with compass needles and magnets. Now, if we take away the magnet for a moment, what's going to happen? If we take this away, let's just delete it. Then what you'll find is this thing, which we had over there, is going to turn, and it's going to go back to the direction it was originally facing, which is the Earth's magnetic field. Now, what do we know about the Earth's magnetic field? And I saw some geography answers there that were being given. So let's just illustrate them and let's explain what's happening inside the Earth. So if that's the Earth, and I know that this is not a geoid, but it's more of a circle, we know that at the moment, well, let's just shape it a little bit flatter. At the moment, we're over here. We're in the southern hemisphere. We're down here, and we call this the southern hemisphere. This is the South Pole, geographic South Pole. That's the geographic North Pole. But what we do need to recognize is that at the core of the Earth, right down at the middle of the Earth, we think that there is a center core made up of iron. And it's not solid, it's liquid, and it's spinning. Now, if you've got spinning iron, molten iron that's spinning, it will generate a huge magnetic field. And because it's spinning, it's creating this magnetic field, and what we need to recognize is it attracts all other magnets in a particular direction. So now let's come and put our little compass needle over here, which I want to move, my compass needle, and I want to put it on Earth. Where does it point to? It points to the geographic north. We've called this geographic north. But what do we know about the nature? We know that that's a north pole. And what do we know about magnets? North is attracted by what? Is north attracted by north?
No.
North is repelled by north.
By north, yes.
Okay. So north is attracted by south. And this is where it becomes confusing. What you need to recognize is that even though we call this north geographic, and I'm just going to put it geographic like that, in fact, the nature of this magnetic pole that sits a little bit to the side is actually the nature of a South Pole. It's a South Pole magnet. So if we have to draw the magnetic field of the Earth, what would we recognize? That at the geographic north and at the geographic south, this is geographic, that the nature of the poles is actually the opposite. So the magnetic pole goes around like this, just like a big bar magnet. But now what do we need to recognize? That the field lines run towards the geographic north. And if the field lines run in 3 dimensions towards the geographic north, let's just clear that up and make sure they're pointing to the geographic north like that. They're running towards the geographic north. Let's not move it. They're running towards the geographic north. We recognize that anything that runs away, remember what we said earlier? If it's coming in, then this is a south magnetic pole. And this, where it's coming away from, is a north magnetic pole. So actually, the world is upside down. What you thought was north is actually south. And what you thought was south is actually north. But hang, that's quite a statement for the moment. And it could put you in a bit of a spin. Please don't get your geography teachers confused. North is still north, but we call that geographic north. We call down at the Antarctica. Antarctica is the South Pole, geographic South Pole. The nature of that magnetic field is that the field lines run from south to north. So that means what we say is geographic south is actually a magnetic north. And the thing that's at the top of the earth in the northern hemisphere is actually a south pole, because it's attracting all the little compasses to go to the north.
So in other words, the Earth is like a big magnet.
The earth is a big magnet, absolutely. So when we asked where do we find magnets at the beginning, here on earth, there's a huge magnet that comes from that core, that iron core at the middle of the earth. Okay. Okay, shall we take some more questions?
Yeah, sure. Let's check this one. What is the difference between magnetic North Pole and the geographic North Pole?
Have we explained it?
A little bit more.
Okay, so what we need to recognize, the geographic north is the thing that we say on the map. Okay? It is, in geography terms, at along the point of 0 latitude. If I'm right. No, 90. I can't remember. 0 is the equator, 90 is at the 90 degrees north. Okay, that's the geographic North Pole. Now, there is a magnetic north in terms of geography reasoning. And that's slightly off that symmetry of nice longitude and latitude. But in terms of the physics, in terms of the science, those rocks are actually South Pole rocks. Okay? They're attracting North Poles towards them. So if we took our little compass or our little magnets, and this was the North Pole and this was the South Pole, and we went up to that rock, we would find that it would attract the South Pole and it would repel the North Pole. Okay? Be very clear about that. So the Earth is a giant magnet. I hope we've gone over that.
Okay. What is the difference between a ferromagnetic material and domains?
Okay. So ferromagnetic material is something that contains iron. Domains happen in all material. So whether we've got something like zinc, it has a domain. It has magnetic domain. Or copper or aluminium. But the domains are not aligned. Now, here's an interesting thought. Again, the word ferromagnetic isn't really required in the syllabus, but it contains iron. But it's not the only type. It's the most common type of magnet. It's not the only type of magnet. We get a whole lot of other materials. There's one here that you might be interested in AB.
Mm-hmm.
Did you know that oxygen is actually magnetic as well?
Nope.
Okay.
Very interesting.
Here is the idea that if you take liquid oxygen and you put it between two powerful magnets, it will stick to the ends of the magnet. Okay. It will be pulled to the one side. It will attach itself to magnets. We don't think about it, but it is called paramagnetic. Okay. So it gets ferromagnetic, paramagnetic, and then the rare earth magnetics as well. You don't have to worry about all of those terms. Understand the most important thing. Permanent magnets, where those domains are aligned all the time, and temporary magnets, where if you bring them into a strong magnetic field, they will remain aligned. Other material, they won't be affected by magnetic fields. The domains are random and they will stay random. They won't align themselves. Okay, because of their electron structure. It's not possible for them to become magnetic.
Okay, so are ferromagnetic also the same as alloys?
No, alloys are a mixture of metals. And when we've got ferromagnets, then we're saying we've got iron mixed into an alloy. But not all alloys have iron. So for example, brass or bronze doesn't necessarily have iron in it, but it is an alloy. Okay.
Cool. Let's take the last one quickly. What is the difference between ferromagnets and permanent magnets?
Okay. Remember what we've said. Not all things that are iron are permanent magnets. So your pin that you stroke will lose magnetism over time. Soft iron particularly loses magnets over time. Hard iron will retain its magnets. I think I've answered the question.
Awesome, you did. Well, thank you. That's where we have to end it today.
It's a pity. Guys, don't forget the test yourself questions. They'll be coming up shortly.
Awesome. They'll be on facebook.com/LearnExtra and still follow us on Twitter @LearnExtra. But for today, that's where we end it. We hope you have enjoyed yourself and still consult us whenever you're struggling. We love you, Mindsetters, and peace.